All right, so we're going to look at a relationship here called the work-energy relationship and how it applies to our situations. So what does work do? Well, there's two types of forces. There's the external forces, and those are the applied, normal, tension, friction, air resistance forces, forces that we talked about with Newton's laws. Then there's internal forces, okay? And these are forces that come from inside, right? The external forces are things that are done to it. The internal forces are those that are inside the object, like gravity, magnetic, electrical, or even the spring force. So we have external and internal forces. Now, this is where it's important to understand. When net work is done by an external force, so when one of our external forces does work, we change total mechanical energy. It's not conserved. Okay? It's changed. If the total work is positive work, then it will gain mechanical energy. If the work is negative, it will lose mechanical energy. Now, this loss of mechanical energy can be either potential, kinetic, or both, depending on the situation. And we'll look at some situations so you can understand that better. But now, for energy to be conserved totally, the work that is done will be equal to the change of mechanical energy. So work that's being done by the external forces will equal the change in mechanical energy. So total energy is conserved, but mechanical energy is not. So because external forces can change total mechanical energy, another word for those are non-conservative forces. So external forces, applied, normal, tension, friction, air resistance are also called non-conservative forces. Now, there are also forces, right, when the only type of force doing net work upon the object is an internal force, gravity, spring, etc., total mechanical energy is conserved. So energy changes form, but kinetic and potential energies remain constant. Energy conservation is what that is called, okay? Total energy being conserved. All right? Which is always true. But in this case, total mechanical energy is always conserved. When the only forces doing work are internal forces, energy changes forms, kinetic to potential or potential back to kinetic. Yet total mechanical energy is conserved. Because internal forces cause conservation of total mechanical energy, we call those conservative forces. Okay, so you have non-conservative and conservative forces. So here's an example. We got a ball at 2 meters and it starts to fall. At the top we have potential energy. That potential energy is getting converted into kinetic energy. Okay, if there was air resistance, then we'd have something to talk about with work, but there's no work being done. So this is strictly potential to kinetic, because as it drops, it's going to go faster. And as it gets closer to the ground, potential decreases while kinetic increases, but total energy stays constant. So we got a skier at point A and goes down the hill and then back up to point B. So at point A, potential energy. At point B has some potential. But since it's moving, it's also going to have kinetic. But we know that the potential energy that I start with equals the potential plus kinetic that I end with. Total mechanical energy is conserved. Okay, again, no friction, therefore there's no work being done. Baseball's traveling upward towards a man in the bleachers. So what's going to happen if you throw a ball in the air, its velocity will decrease. And that helps us with energy, because down here, total kinetic energy. But as we go up, kinetic energy decreases because velocity decreases, and potential energy increases because height increases. And again, the change in the kinetic energy gets converted, if you will, into potential energy. This one's kind of tough. We got an upward force on a falling bungee jumper, okay, which in turn is going to slow down. So it's going to decrease kinetic energy because you're slowing down. At the very top, okay, at the very top, you're going to have a lot of potential. But as you drop, you're also going to have some potential. So at the very top of your jump, you're going to have potential energy. But as you drop, you're going to have kinetic plus potential. But your speed's decreasing anyway. But total energy, again, going to be conserved. Now, positive and negative work and how that relates to energy change. When we have non-conservative forces, okay, total mechanical energy is not conserved. The work can be positive or it can be negative. And that just depends on direction. Is the force going in the same direction as displacement, or is the force going opposite of displacement? That's positive, that's negative. Angle 0, angle 180. In the same direction, positive. And if positive work is done by an external force, right, then the object gains mechanical energy. So positive work means gain in mechanical energy. If you have negative work, the object loses mechanical energy. And it gets converted into something else. Probably heat in most cases. So Megan drops the ball and hits it with the forehand. The racket is moving horizontally as the strings apply a horizontal force while in contact with the ball. So we're applying a force this way, right? And the ball travels that way, therefore positive work. Mechanical energy will increase, usually in the form of kinetic energy, because the ball's going to gain velocity. Here we got a player hits a ball off a tee. We got a little angle here of 10 degrees, okay? But our force is going that way and the ball is going to travel this way. Therefore, our work is positive, which means our mechanical energy is going to increase. Now, what is that mechanical energy going to become? Well, it's definitely going to become kinetic energy because of the speed. But since we're also hitting up, it's going to gain some with potential energy. So that work is going to get converted into kinetic and potential energy. Well, on the first one, since our ball stayed horizontal, it's converted into kinetic energy. Okay, we're hitting a nail into a block of wood. The hammer is horizontal. Therefore, the hammer is going this direction, and the force is being applied that direction, and the nail's moving in that direction. Therefore, positive work. Okay, even if it's going to the left, it's still positive because we're going in the same direction. And since the nail's going to gain speed, it's going to become kinetic energy. So this positive work is going to become kinetic energy. Now, we got a car moving this way, and our brakes are applying a force this way. There's our first example of negative work. Okay, and since the car is slowing down and it stays horizontal, the only thing that's changing is kinetic energy. So kinetic energy of the car will decrease. Potential energy will stay constant because our height is still constant. So we're pushing off, our diver's pushing off of the stand this direction. Diver's also going to move that direction. So force and direction, so it's going to be positive work. This positive work is going to cause an increase in velocity. So our kinetic energy is going to increase. So this work is going to make our energy increase. So it's going to become kinetic energy. And then lastly, we have a weightlifter lifting up the object. So the force is going up and the object's going up. Positive work. If we have positive work, that means we're going to gain potential energy. And it's not kinetic energy because it's moving at a constant speed. So we're gaining potential energy because we're gaining height. But in all cases, work is being converted into potential or kinetic energy into mechanical energy. So here's how we can figure this all out, right? We know that this guy's lifting up with a force of 1,000 newtons, and the distance is going to be 1/4 of a meter. So we know that since they're going in the same direction, our angle is going to be 0. So our work is 250. So our total mechanical energy initially is 1,500. We add 250 joules, okay? Makes our final energy 1,750 joules, with that 250 joules being work done, but it's also increasing potential energy. Catcher catching a baseball. The force that's being put on the glove is 600 newtons. The distance the glove or the catcher moves back is 0.1 meters. Again, we got a force going forward and the distance going back, which leads us to 180 degrees. So when we do the math for work, we get negative 600 joules. So if the initial energy is 605 joules, but we lose 600 due to work, our final energy of where the ball stopped is only 5 joules. Here we got a car. The car is going to have a force going this way while it travels this way. Okay, again, that's going to make our angle 180. Force of 8,000 newtons times our distance of 30 meters times cosine of 180 gives us negative 240,000 joules. That's the external work being done. Initially, we have 320,000 joules of energy. The energy that the car has after we lose some to the braking is 80,000. And that's going to be all kinetic energy. Just because the car is slowing down, velocity decreases, therefore kinetic energy decreases because of the work being done by the brakes. Here we're pulling up an object up a slope. And since they're on the same plane, right, our angle's 0. Okay, don't worry about this angle, not important as long as they're on the same plane. 18 newtons of force, 0.7 meters times 1, 12.6 joules. Initially, we had no energy. We did work of 12.6 joules, which in this case is going to be, I'm guessing since we're going at a constant speed, would be its potential energy increasing 12.6 joules. But we're doing work externally. I know that's a lot to take in. If you have questions, please see me.